Hey, welcome back. So this is lab 5 for physics 2211, and this is the choose your own adventure lab, and I chose to do it on a slinky drop. So go to the next slide here. So a little introduction to the lab. Basically the overall purpose is to compare how the slinky drops in total. So it's going to be elongated from the top to the bottom and then drop from the top, and then we're basically going to explore how that motion of the object, specifically the bottom of the slinky, moves. So that's what we're going to answer in this lab. And just a little preview of the results. So basically what happens is the top of the slinky is dropped and it's moving downwards towards the bottom, and the bottom of the slinky remains stationary in the air, like completely exactly where it is until the top of the slinky reaches that, and then they move downwards together. And then when comparing a computational model to a tracked experiment, the computational model is just a little bit more precise and smoother, as the tracked one is a little bit more inaccurate. So some main physics ideas just to be used in this lab. So of course, Newton's second law, net force is equal to the change in momentum over time. That's a big one in this lab as the spring moves downwards. And then drag force is also used in this lab. That's taken into account in the simulated experiment. And then gravitational force is taken into account in both the simulated and the experimental. And then the position and velocity update formulas are big in this, as we're tracking how the top or how the bottom of the spring is going to move. And so once we get basically can convert these into glow strip code. That's how we create the simulated experiment. So here's the experiment right here. So you can see this is as the slinky is dropped all the way to the bottom, but he's holding the top of the slinky right here, and the bottom of the slinky initially starts right here. And then as the top falls, the bottom remains right here until the top hits, and then they both move downwards. And that's what these red dots are where I tracked it. So the initial conditions, the mass is 0.25 kilograms, and then the initial position and velocity is both 0, 0, as the bottom is right here on this point where I created my axis 0, 0. And then the initial velocity is of course 0, as the top is moving, but the bottom is completely still at the beginning. So here's as comparison, here's the simulation. So I'm going to run through just a little bit of the glow script code here. So the initial slinky mass was 0.25, like I just said in the last one. And then the initial position and velocity we defined, as well as the delta t I defined, to basically get the same amount of data points for both the simulation and the experiment, so I could compare the two on a graph. And then set acceleration for gravity is 9.8, like I defined earlier, as well as we found the drag constant to be 2.6. Then into the main part of the simulation. So it's the while loop as the top of the slinky is moving, but the bottom is stationary. So I found that time to be 0.265 in the video right here. So I created this while loop to end right there. Basically, I defined the work, net force, and force, and the most importantly, the velocity update and the position update formula. I basically set to be those formulas that we were talking about earlier, and then advance the clock, plotted the line on the curve, a lot of stuff like that, just to make sure it outputs it. And then here's the second part here. So after the top has reached the bottom of the slinky and they're both moving simultaneously, and then up until the point where they hit the ground. And so again, I define the work and net force, and then set the velocity and position updates. And so really the only difference here is going to be the top of the while loop. And then let's move on there. So now here's the results here. So here's the tracked experiment. You can see all the data points I have right there versus the simulated experiment. This is the graph from the glow script. This one's just a little bit more smoother, and you can see as I put them both in Excel and basically compare the two. The simulation is just overall a little bit more smooth, and then the tracker has a little bit of like kind of parity to it, and then ends a little bit higher than the simulations basically expected. And that's because the simulation is just more accurate. So that's what I kind of explained here. So basically the experiment had a little bit more parity to it than the tracker did, or than the simulation did. And then some basically why this could happen is the mass of the slinky could be off, or I wasn't able to use a calibration stick on this one just because I didn't know any heights in the video. And then I also could have mistracked just a little bit just because the video wasn't at a higher frame rate than I would have liked. So what does this all mean? Basically the computational model doesn't really understand how the top of the slinky is moving until the bottom hits, because I'm only really accounting for the bottom there. And then yeah, like I was talking about earlier, the bottom of the slinky remains still until the top hits it. So what if we replace the top of the spring with a weight? Basically what would happen is nothing different would happen, because this force upwards on the bottom is the same as the gravitational force downwards on the bottom, and that's why it stays still at the beginning. And thank you very much.